California's earthquake problem just got worse. Triple quakes just struck the Bartlett Springs Fault, and they landed on a fault most people in the state have never even heard of. It's called the Bartlett Springs Fault. It runs for roughly 100 miles through the coast ranges, and the quiet truth about it is that it is capable of producing a magnitude 7. What just happened there is not on its own a disaster, but it may be a signal. And once you understand what's actually loading up beneath Northern California right now, you're going to look at this whole region differently. So let me walk you through exactly what struck, where it struck, what kind of movement caused it, and why a growing number of these quakes over the past year point towards something bigger waiting in the wings. Start with what just came in. A magnitude of 4.4 struck north of Cabello in Mendocino County. And almost on top of it, within about a minute, a magnitude 3.9 hit nearly the exact same spot. There was a third event mixed into that same window that briefly appeared in the catalog before being revised out, which is completely normal in the first hours after a sequence, as seismologists refine the data. And that's an honest thing worth saying up front. These early magnitudes shift. A quake, he can arrive as a 4.5 and settle at a 4.4 once the review is done, and different agencies sometimes disagree on the same event, so treat the exact decimals as provisional rather than gospel, but the location is not provisional. It's right on the Bartlett Springs Fault system, and that's what makes it matter. Here's the part that turns a single cluster into a pattern. This wasn't the first jolt in this exact area. Back on the 11th of July, another magnitude 4.4 struck just north of Cabello, and the U.S. Geological Survey formally flagged that one as the potential main shock of an earthquake sequence, which is significant language. Then, a few days before that, on the 28th to 29th of July, a magnitude 4.2 hit near Cloverdale, further south along this same connected web of FA faults. And looming over all of it, back on the 24th of June, a magnitude 5.6 struck near Redwood Valley in Ukiah, out on the Macama fracture zone. That 5.6 is believed to be the largest earthquake ever recorded in that particular zone in the modern instrumental record. So when you lay these out together, a 5.6, a 4.4, another 4.4, a 4.2, and now this fresh pair north of Cabello, you're looking at an unusual amount of energy release for this region packed into a remarkably short stretch of time. And to really appreciate how unusual that is, you can't just look at the past few months. You have to zoom out across years, even decades, because that's the only way the abnormality reveals itself. This is exactly the kind of clustering that seismologists watch closely, because bigger earthquakes very often announce themselves with smaller ones first. Not always, and I'll come back to that caveat, but often enough that a run of acti, vidi like this, deserves genuine attention. The reason it's worth taking seriously here specifically is the length of these faults. Both the Macama and the Bartlett Springs Fault stretch 100 miles or more, and fault length is one of the single biggest controls on how large an earthquake a fault can generate. There's been excellent scientific work mapping these structures out, but here's a humbling reality of the field. You often don't learn the true extent or the true danger of a fault until it produces a large rupture. The perfect and painful example of that happened in 2014 when a magnet, U6, struck Napa. The West Napa fault that produced it wasn't even well recognized before that earthquake tore through. It caused roughly $1 billion in damage, and part of why Napa shakes so hard is that its underlying geology amplifies seismic waves, concentrating the energy right where people live. In hindsight, the fault seems obvious, but that's how these things go. The ground keeps secrets until it decides to reveal them. And that's the uncomfortable frame to hold as we look at these two faults running parallel to the Great San Andreas. They're shorter than the San Andreas, and generally considered less destructive. But there's a real case that they're a bit more dangerous than current estimates suggest. Because, under the right conditions, certain sections could rupture together, or rupture in concert with neighboring segments, and produce a larger event than the simple math would predict. The working estimate is that both of these faults are capable of a magnitude 7, possibly under the worst circumstances even more. Now let me explain how these faults fit together, because it's the connection that matters. The Bartlett Springs Fault and the Macama Fault are not independent players. They're subsidiaries of the San Andreas system, all part of the same vast machine grinding the Pacific Plate past the North American Plate. The San Andreas takes on the majority of that plate motion, but not all of it. A meaningful share, somewhere in the range of 10 to 20%, gets absorbed off to the east through the Walker Lane shear zone and across the basin and range. And another tantial chunk is carried by these subsidiary faults right here in Northern California. They're not as long or as capable as the San Andreas, so their maximum earthquakes are smaller. But as you trace them on a map, some of these faults run for a very long way, and because they're all interconnected, what happens on one genuinely influences the others. Strain doesn't stay politely in one lane. For scale, think about the earthquakes that struck Venezuela this year. a magnitude 7.5 and a 7.2. That rupture ran on the order of 100 to 200 miles of fault. Once a fault reaches that 100-mile class, magnitude 7s become physically posses. Bill. So when I tell you the Macama runs over 100 miles, I'm telling you it sits in exactly that size class. And here's a detail that should stop you. The Venezuela earthquake struck on the very same day as that magnitude 5.6 near Willits in Northern California. Now, the two events are on opposite sides of the planet and are not causally linked in any direct sense, but I mention it because the Venezuela faults were known from a 2018 scientific paper to be near their final critical stage. Researchers understood those faults were loaded and overdue, and yet there was no obvious little foreshock swarm politely announcing the rupture beforehand. It simply, penned, which is the caveat I promised. Sometimes the big one arrives with warning, and sometimes it just goes without any preamble at all. The activity we're watching in Northern California could be preliminary signs, or the real event, if it comes, could arrive without any further heads up. Both are true at once, and honesty requires holding both. Right in the middle of this whole picture sits something remarkable that acts almost like an engine. It's called the geysers, a remnant volcanic system south of Clear Lake, and it's one of the most seismically busy spots in California. It produces a steady drumbeat of small earthquakes, magnitude 4s, 3s, and 2s, essentially, nonstop, driven by hydrothermal fluids moving through hot rock. Over the past year and a half, it's thrown out a whole string of magnitude 4 events. And here's why: that's not just background noise. The geyser sits right at a critical junction where 3 faults converge south of Clio. R Lake. That is not a coincidence. That volcanic system is continuously loading energy not only onto the San Andreas, but onto these neighboring faults. And that junction is the doorway into what I'd call true Northern California. So this constant low-level activity may be quietly stressing the very faults we're now watching light up. Now let's put a real timeline on how rare this is, because this is where the pattern becomes undeniable. Look at the Cloverdale area first. That recent magnitude 4.2 is notable, and when you check the long record going back to the year 2000, the only comparable events, a 4.2, a 4.3, and a 4.6, all struck within about a week of each O. They're back in January of 2000, plus a lone 4.0 in 2003. In other words, the recent quake is essentially the first magnitude 4 or greater to strike that spot in more than 2 decades. That's separate from the constant chatter at the geysers, which is its own beast. This is a distinct fault system waking up after 20 plus years of relative quiet. Then there's the Macama site of the 5.6, which stands as the largest event in the entire record we have for that zone, surrounded by only a scattering of 4s across the previous couple of decades. And up near Covelo, essentially every earthquake on record has come in just the past 5 years, with 2 of them landing within roughly the last month. Step back, and the shape emerges. Energy has been migrating northward, up from a 4.3 near Berkeley in September 2025, to a 4.0 near Glen Ellen in December 2025, and on into this cluster of activity in the far north. It reads like a progression, not a coincidence. There's one more clue from that 5.6 that I find fascinating, and it's the kind of thing that reminds you an earthquake reshapes the actual ground beneath your feet. After that quake, reports came in of any spring activity across the area. Springs that had been bone dry suddenly started flowing. Wells that had been producing modestly began gushing. What happened is that the rupture shifted the plumbing of the water table, cracking open fresh pathways and fractures for ground, water to rise. So around Redwood Valley, you now have this strange silver lining, an outpouring of water revitalizing a dry landscape, all because a fault slipped underground. It's a vivid physical illustration that these events don't just shake buildings, they rewire the Earth's interior. So what kind of motion actually caused these quakes? This is where the focal mechanisms come in, and they tell a consistent story. Today's magnitude, 4.4, came through as a nearly pure strike slip event with just a touch of extension mixed in, meaning the 2 sides of the fault mostly ground horizontally past one another with a slight pulling apart. The 5.6 on the Macama was almost textbook strike slip. The Cloverdale 4.2 showed the same fundamental character. And critically, all of these faults, the San Andreas, the Macama, and the Bartlett Springs, are right lateral strike slip faults. That means if you stood on one side and looked across, the far side would appear to be moving to your right. And the same is true looking back the other way. They're all shearing in that same right lateral sense, one after another, like a series of gears set at an angle to the plate boundary, each grinding in the same direction. One thing that struck me about today's event was how far the shaking traveled. The "did you feel it" reports came in from as far away as Eureka and McKinleyville, well to the north. Most of those distant reports described only weak shaking, and closer to the epicenter, people felt light to moderate shaking, but the sheer spread of it was surprising for a 4.4. It shows how efficiently the energy dispersed along the structural grain of the region. Compare that to the 5.6 though, and you understand instantly what an extra magnitude and a half really means. That larger quake drew thousands upon thousands of felt reports, with many people describing strong and even very strong shaking. A 5.6 is fully capable of cracking chimneys, knocking houses off foundation, and causing real structural damage. The difference between a 4 and a 5.5 isn't a small step. It's a leap in released energy. And it's exactly why the jump from what we're seeing now to what could be coming is worth taking seriously. Let me be precise about the slip rates, because they explain both why these faults are slow and why they're still dangerous. The Bartlett Springs Fault creeps along at roughly 1/4 of an inch per year. The Macama moves at around 8 millimeters annually, within a geological range of about UT 6 to 10. Across the whole Northern California plate boundary system, something like 33 to 37 millimeters per year of strain accumulates, with roughly 5 to 7 of that loaded specifically onto the Bartlett Springs system. These are not fast-moving, tiny-moving faults, but slow does not mean safe. It means they build strain patiently over long stretches of time and then release it all at once. A fault can spend a century quietly loading and then unload in 15 violent seconds. That's the nature of the threat here. It's the slow, steady accumulation that makes the eventual release so powerful. When you pull way back to a fault map of California, you can see how all of this interconnects. Near Santa Rosa, multiple faults braid together: the San Andreas, the Rogers Creek Fault, the Macama Zone, and intermediate strands like the Alexander and Redwood Hill faults, all knotting up in one heavily sheared REA. And that kind of tangled junction is precisely the setup you'd want to watch if you were worried about a simultaneous rupture across more than one fault, because that's genuinely possible. If the Rogers Creek and Macama faults were somehow to rupture together in a single linked event, you could push the magnitude to Ward 7.5. As a rule, the longer the fault sequence that breaks, the larger the earthquake it produces. Further north, the Bartlett Springs Fault runs from the Clear Lake area all the way up toward the Round Valley Reservation as a system of multiple traces, and to the south, it links into the Bressa Fault system and beyond. The overarching truth is that Northern California is threaded with faults running parallel to the San Andreas, and while enormous strain loads onto the San Andreas itself, these neighboring faults have their own accumulated stress that has to release eventually. Now, when will any of this actually happen? That's the question everyone wants answered, and honesty demands I be careful here. I can't give you a date. Nobody can. And anyone who claims to is selling something. Geological time and human time usually run on completely different scales. It's entirely possible that a magnitude 7 on the Macama is 100 years away, and that a 6.8 on the Bartlett Springs is 200 years out. But it could also be dramatically sooner. What I can tell you is that these are meaningful data points, not proof, but signals worth respecting. And there's a rhythm to consider. California appears to move through roughly 35-year cycles of heightened and reduced seismic activity, and by that reckoning, we're still within an elevated window that includes Ridgecrest in 2019 and Napa in 2014. We may be starting to come down from the peak, but statistically we remain likely to see a significant event sooner rather than 15 years from now. If I'm being straight with you, a magnitude 6 or 7 somewhere in this system before the end of the decade is well within the realm of the plausible. The San Andreas itself is famously overdue, and its long dormant southern segment hasn't ruptured in more than 220 years. That one, when it goes, could produce a magnitude 7.5. It's all a matter of time. Here's a subtle point about that 5.6 that genuinely keeps me uncertain, and I want to share the uncertainty rather than paper over it. Normally, when a quake is the event that fully ruptures a fault, you get a healthy swarm of aftershocks afterward as the fault settles, essentially the sound of the fault relaxing. But the 5.6 near Redwood Valley produced only a handful of small aftershocks, a 3.8, a couple in the 2s. That relative quiet afterward is actually more consistent with the 5.6 being a foreshock than a main shock, because a true fault-clearing rupture tends to liberate a lot of fracturing and micro events, and this one didn't. It's not conclusive, but given how overdue these faults are, the muted aftershock response is at minimum very interesting. And it's one of the reasons I can't rule out that the largest event in this sequence hasn't arrived yet. And this all sits inside a bigger global context that I crunched the numbers on, because a lot of people have been asking whether the last couple of years have felt seismically abnormal. The short answer is that they have. Looking at cumulative global seismic energy from 2020 through August 2026, counting all earthquakes magnitude, 5 and greater, the picture is striking. The year 2025 released around 334 terawatt hours of cumulative seismic energy, close to triple the next highest year in that span. That spike is driven heavily by the magnitude 8.8 that struck off Kamchatka in July of 2025. The largest earthquake anywhere on Earth since the 2011 Tohoku disaster in Japan, and among the largest ever recorded. Energy scales dramatically with magnitude, so a single event that size dominates the totals. By comparison, 2024 was remarkably quiet, and 2022 was quieter still. And here's the kicker. We're only 2/3 of the way through 2026, and the year has already surpassed the full year totals of both 2024 and 2022, running more than 50% above 2024. The planet has been unusually energetic since roughly mid-2025, and it hasn't calmed down. Why does that global picture matter for a fault in Northern California? Because energy is connected. When a magnitude 8.8 ruptures off Kamchatka, or a 7.5 and 7.2 strike Venezuela, those events send seismic waves rippling across the entire planet. And studies have already documented that the Kamchatka quake triggered increased seismicity as far away as eastern North America. Every one of these large ruptures nudges stress into faults far from the epicenter. Add in the relentless activity at the Mendocino Triple Junction off California's northern coast, and you have energy being loaded into the interior of Taditapatete, a state from multiple directions at once. And here's the plain truth underneath all of it. When the whole world is this active, quieter regions like California, which people think of as extremely seismic, but which is actually calm compared to places like Japan or Greece, start to feel that elevated global backdrop too. Everything has to balance out eventually. Eventually, Cascadia will produce its magnitude 8s or 9s. Eventually, California gets its next big one. Eventually, these faults beside the San Andreas release their mid-6s and 7s. It is all simply a matter of when. So let me tell you what I'd actually watch over the coming weeks and months, and it comes down to 3 things. First, the maximum magnitude. If activity in this system stays capped around the mid-4s, the current interpretation of ordinary fault loading holds steady, but a jump toward magnitude 6 would signal that a much larger process has engaged. Second, the aftershock behavior of any significant event. A quake that's followed by a vigorous swarm has likely done its job and relieved the fault. A large quake followed by eerie silence, like that 5.6, is the one that makes seismologists nervous about what might still be waiting. And third, the geometry and the northward march of the epicenters. If the activity keeps creeping up the Bartlett Springs and Macama trends, that migration itself is information worth tracking. To bring it all together, 3 earthquakes just struck the Bartlett Springs Fault, a 100-mile structure quietly capable of a magnitude 7, and they're part of a genuinely unusual run of activity that includes the largest quake ever recorded on the neighboring Macama zone. That doesn't guarantee a larger earthquake is imminent. Nature keeps its own calendar, and the caveat cuts both ways. Warning or no warning, it will happen when it happens. But the signals are real, the faults are loaded, and the global backdrop is more energetic than it's been in years. My honest read is that Northern California is more likely than not to see a significant event before this decade is out. And the responsible response to that isn't fear, it's preparation. If you live in this region, keep a 72-hour emergency kit ready to grab and go. Keep water on hand. And consider a backup battery so a multi-day power outage doesn't leave you stranded. Be smart, stay vigilant, and then go enjoy your life, because readiness is what lets you stop worrying. Take care of yourselves out there, and I'll be back very soon with the next update.